Hello everyone, this is Professor Roman. Let's continue the group theory lectures. In the previous lecture, I talked about the course itself, and I promised that the first chapter of the book would concern context. I want to try to place group theory into the context of abstract algebra in general. So, what is abstract algebra? Well, in simple terms, abstract algebra is the study of non-empty sets that are given an algebraic structure, which is defined on the set by specifying one or more algebraic operations. Some of these operations are called addition, some are called multiplication, some are more unusual operations that don't fit really either of those terms, and we'll discuss that a bit later. But we will see that the operations, however they're described, must possess certain properties, such as associativity or commutativity. When a set A has been given an algebraic structure, the set is called the underlying set or the carrier set for that algebraic structure. So an algebraic structure consists of three parts: a non-empty set A called the underlying set or carrier set for the structure, one or more algebraic operations defined on the carrier set, certain specified properties that are required of the algebraic operations. Perhaps the most famous algebraic structure is that of the real numbers, along with the usual algebraic operations of addition and multiplication, and their well-known properties. For example, addition is associative, it's commutative, multiplication also associative, commutative, and so on. But as you probably know, the set Mn of R of all real n by n matrices is also an algebraic structure under the familiar operations of addition and multiplication of matrices. Also, the set of all functions on the real numbers, for example, is an algebraic structure under the familiar operations of addition and multiplication of functions you would have studied in calculus. Another familiar algebraic structure is given to the power set, P of S, of a set S, by defining the algebraic operations known as union and intersection. Now, it's very important to understand that the carrier set alone is not an algebraic structure. Both the operations and their required properties are part of the structure. As a matter of fact, a single non-empty set can generally be made into many different types of algebraic structures by defining different algebraic operations on the set, or even just changing the required properties of the operations. For instance, the set Z of integers, together with the usual operations of addition, and the integer 0, and we'll see later that is actually an operation, it's called a Nullery operation, is an example of a structure known as a monoid. But the set Z together with the usual operation of multiplication and the integer 1 is a different monoid. Same carrier set, but different monoid, different algebraic structure. The customary formal notations for these monoids look like this. This is an ordered triple, carrier set, one operation, the other operation, binary, nullery, as we'll discuss. And this is the notation for the other monoid. I'll define monoids for you formally later in the book. The reason that this structure is a monoid is that the operations have the following two properties that are specified in the definition of a monoid. Addition must be associative, it looks like this, and the element 0 must act as a neutral element for addition, and that looks like this. When you add 0 to an element A in either order, you just get the element A. So that's a neutral behavior. Similarly, the reason that this structure is a monoid is essentially the same reason. Multiplication in this case is associative, and the element 1 acts as a neutral element. These are only two examples of monoids, and we're going to encounter others later in the course. Monoids play a significant role in other areas of mathematics, and also in computer science, for example. It's very simple algebraic structure, two operations, but quite useful. In fact, a group is a special type of monoid that is required to have one additional algebraic operation called the taking of inverses. And we'll go into that again at the appropriate time. I'd like to emphasize, because I know some students will be confused at first, that the carrier set of an algebraic structure need not be a set of numbers. And most of the time it's not. The carrier set is often a set of functions, matrices, some other type of mathematical object. On the other hand, you might be surprised how many unlikely candidates can serve as the carrier set for a useful algebraic structure. Just as an example, some linguists study the syntax and semantics of language by defining an algebraic structure on the set of words or phrases or even the set of thoughts in a given language. And this construction plays an important role in the field of artificial intelligence. Group theory, for example, also plays a role in music theory. For instance, the pitch classes in an equally tempered octave form a group with 12 elements. As we will discuss in a moment here, in the general study of a particular type of algebraic structure, such as groups, for instance, we often think of the elements of the carrier set merely as formal symbols. We assign them no intrinsic meaning, mathematical or otherwise. And we refer to a generic or unspecified group, namely a group whose elements are formal symbols, as an abstract group. And of course, the purpose of studying abstract groups is to establish properties that apply to all groups. Since any property that we can establish for an abstract group will apply to all groups because it doesn't depend on the nature of the elements of the underlying set. Now, on the other hand, the nature of those elements for a specific situation do play a key role in determining whether or not the properties that are required by a given algebraic structure actually hold for that particular set. So, as a concrete example, if we wanted to show that multiplication on the set of 2 by 2 real matrices is associative, we will, of course, need to use the properties of matrices. But once we've determined that that set is, say, a monoid, then the fact that the elements are matrices is no longer relevant to the monoid properties of that structure, such as, for example, the uniqueness of the identity element. One can prove that in all monoids the identity is unique, and I'm going to do that. And therefore, once we've established that a particular set, say, of matrices is a monoid, the fact that the identity is unique has nothing to do with matrices at that point. Which matrix is the identity? Of course, that does have to do with the nature of matrices. But once the set is established to be a monoid, we've established that there is an identity matrix. Then the uniqueness of that identity matrix follows from monoid properties, not from properties of matrices. I hope that made sense. It may take a little thought there to grasp this, but it is fairly important. With the exception of the operation of scalar multiplication that's required in the definition of vector spaces and also modules, the algebraic operations that are generally studied in abstract algebra are one of three types, and they're defined as follows. Capital A will be a non-empty carrier set. A nullery operation on A is just an element of A. A unary operation on A is a function from A to itself. And a binary operation on A is a function f from A cross A to A. So it takes ordered pairs from A cross A and produces single elements of A. Now you might be wondering why anyone would bother to refer to an element of a carrier set as a nullery operation. Why not just call it an element? Well, that's a fair question. The reason is to establish both consistency and conciseness in terminology so that the term operation encompasses all the relevant types or ideas that we need to deal with here. In fact, we did that earlier when we defined an algebraic structure as a non-empty set together with one or more algebraic operations and their properties. This language is much more concise than saying that an algebraic structure is a non-empty set together with 0 or more binary operations, 0 or more functions, and 0 or more distinguished elements. You can just say 0 or more operations, and it covers all of those cases. Now you know, if you studied linear algebra, that one of the operations that defines a vector space and also a module is called scalar multiplication. That is can be represented as a function, in, say, for a real vector space, function from R cross V to V. This is not a binary operation because this R here is not V. I suppose it would be considered a form of hybrid operation. I don't know that I've heard that term elsewhere, but it seems like a reasonable one. This table shows some of the commonly studied algebraic structures that form the subject of abstract algebra. There are others, mostly modifications of these. For example, modification of ring that is where more properties are required, there are integral domains, Euclidean domains, unique factorization domains. Those are all types of rings. And they would be studied in a course in ring theory. But these are sort of the basic types. And the table shows, in each case, the number of operations of each of the three types, and also mention of these hybrid operations here, for example. And there's something strange going on for fields, which I'll talk about. The structures that I placed in bold, monoid, group, and lattice, are the ones that will be of most interest to us in this book. Now, that's somewhat of a generalization. For example, we're going to need matrices occasionally, and they form a ring. The integers form a ring, but these are specific examples. In more general terms, monoids, groups, and lattices will be of interest to us. Of course, the main topic of the book is groups. And so monoids and lattices, which do come into the study of group theory, we only need very basic concepts there. So this is by no means a course in monoid theory or lattice theory. We just need to touch upon the definitions and a few basic facts. Now, if you look at this table, you will see that some algebraic structures do not include either unary or nullery operations. Most do, but some do not. But every one of them includes at least one binary operation. Actually, the binary operations form the foundation of the algebraic structure. And the unary and nullery operations, when they are present, generally function in support of the binary operation. And you'll see that in a minute. So these other operations, the unary and nullery operations, are required to interact nicely with the binary operation. And we can see that in the definition of the two monoids I gave you. The underlying set was the integers. I used the language for 0 or for 1, neutral element. Neutral for addition, neutral for multiplication. So the definition of the neutral element depends on, or is given in terms of, the binary operation. As a matter of fact, as I mentioned earlier, the nullery operations in these two monoids are uniquely determined by the respective binary operations, addition or multiplication. So specifically, if 0 and 0 prime are neutral for addition in this first monoid, then the neutrality property of both elements, first of all, we write 0 prime plus 0. If we think of 0 prime as the neutral element, this is equal to 0, but 0 is also the neutral element, so this is equal to 0 prime, and so 0 and 0 prime are equal. Similarly, if both 1 and 1 prime are neutral for multiplication in this other monoid, where to go, right there, then we have a similar argument here to show that 1 equals 1 prime. So as a consequence, we can refer to just these ordered pairs as monoids because the neutral element in each case is uniquely determined. Now let me be perfectly clear. I'm not saying you don't need to verify that there is a neutral element. You still need to do that. All monoids, by definition, must have a neutral element. What I am saying is that once you have verified all the monoid requirements and you state that this is a monoid, go back here, and you write this ordered triple and you say this is a monoid, now you can say, you can refer to the monoid this way, as the carrier set Z with the binary operation of addition, and everybody knows two things. One, you have established there is an identity element, and for some reason you don't feel like mentioning it. And second, that identity element is unique, because identity elements are always unique in any monoid. And I probably wouldn't even be going through this. It may seem like a pedantic discussion here, but you're going to see this in other books. And so it's important to understand that the identity was confirmed for this monoid. We should make one additional point. I see oftentimes students with questions about this. And maybe the best way to do this is by an example. There are a great many, in fact infinitely many, binary, unary, and nullery operations on the set of integers, as an example. After all, by definition, every function, f from z cross z to z, is a binary operation. Every function from z to z is a unary operation, and every integer is a nullery operation. So, for example, this function from z cross z to z is a binary operation, and the integer negative 17 is a nullery operation on z. But these operations are not monoid operations because they don't possess the properties required of a monoid. F is not associative. Negative 17 is not neutral with respect to f. So we have here an algebraic structure, carrier set, binary operation, nullery operation, but it's not a monoid. As far as I know, it's not any algebraic structure. It's a useless, not any given, a specific algebraic structure like ring field and so on. It's pretty much a useless algebraic structure. When studying a particular type of algebraic structure, such as, say, groups, which is what we're going to do, it's important to recognize the distinction between a specific group, also called a concrete group, such as the group of rational numbers whose binary operation is ordinary addition, and a generic group, which is more commonly called an abstract group, as I mentioned before, which consists of a carrier set whose elements are generally unspecified and so are just thought of as abstract symbols, along with the operations required under the definition, of course. This distinction is important because during the study of groups, we're going to encounter two types of statements or theorems. One concerning a specific group or a family of related specific groups, and the other meant to apply to all groups. So, for example, we'll study the so-called Quaternion Group. This is a specific group with 8 elements, which are, at least in the first formulation we're going to give of this group, they're matrices, 2 by 2 complex matrices. And the binary operation is matrix multiplication. So in this case, we might encounter a theorem that begins, let Q be the Quaternion group. So of course, whatever follows in the theorem is a statement about this specific group, and we shouldn't expect it to apply to other groups, such as symmetric groups or dihedral groups or any other type that are not quaternion. We will also encounter theorems that begin, for example, let Sn be a symmetric group where n is bigger than or equal to 3. So this is a theorem concerning a family of specific and related groups. And so again, we wouldn't expect this result to apply to groups that don't belong to this family. On the other hand, many theorems, arguably most theorems in group theory, are intended to apply to all groups. And these will generally begin with a simple sentence like, let G be a group. And that's sort of a shortened form of let G be an abstract group or generic group. So we are now talking about arbitrary groups, and so the nature of their elements is not at all important. We should also make some remarks concerning the notation used for the operations that define a specific type of algebraic structure. So for specific or concrete examples of a group, a ring, a field, whatever, there's often a specific notation. And so I can't really make any general comments about that. For example, we'll study one group whose binary operation is addition modulo n. And I will probably use the symbol here, plus sign with circle around it, sub n. Other authors may use other symbols. Another group will have binary operation multiplication mod n. So again, we need a notation that's specific for that. Here's a group in the exercises. This is not an important group as far as I know, so I left it for an exercise in the next chapter. This set of real numbers different from -1 can be endowed with a group structure, and the binary operation is defined this way. So I used an asterisk here as notation for this binary operation. I certainly don't want to use a plus sign, because if you look on the other side, that would be very confusing. This plus sign, these two plus signs are ordinary addition of real numbers. I didn't want to use just juxtaposition because that looks too much like the product of real numbers. Even a dot would remind us a lot of the product. So I thought a star asterisk would be an appropriate symbol here for this binary operation. Now, on the other hand, abstract or generic structures generally use one or both of the following generic notations. So when you say let G be a group, you're talking about a generic or abstract group. One of these two notations would be appropriate. Under additive notation, the binary operation is denoted by a plus sign called addition, and this is called the sum, A plus B. This is nothing new because it's what you use for the real numbers. Under multiplicative notation, the binary operation is generally denoted by one of either juxtaposition or a dot or an asterisk or maybe some other symbol that I haven't seen could be appropriate. This is called multiplication, and AB is called the product of A and B. The first of these notations, juxtaposition or concatenation, may be the most common. I like it. I use it a lot. But there are times when we need something a little more obvious, such as a star or a dot. and for juxtaposition, sometimes there are readability issues or ambiguity issues, so you may need parentheses, but that sorts itself out usually. Of course, the terms addition and multiplication here are borrowed from the prototypical situation of the real numbers. But as I mentioned before, the carrier sets don't have necessarily anything to do with numbers. You can still use the terms addition and multiplication and this notation. So I know some students have a little trouble with that, but the word addition, it's just a word, and you're used to using it for real numbers and maybe complex numbers, but there's no reason why you can't use it for other binary operations. In fact, you'd use it for matrices and you use it for addition of functions. So why not addition of thoughts if you're a linguist, or addition of chairs if you can figure out some way to add chairs together. There's nothing, of course, prohibiting the use of these generic notations for specific groups, let's say. We add matrices and we multiply functions and so on. Some abstract structures, you can see from the table, require only a single binary operation. And in the generic case, we would use either additive notation or multiplicative notation. And there's a reason we might use one or the other, and I'll talk about that in a later chapter when I define groups. But when you use additive notation for the operations of a group, you call the group an additive group. And when you use multiplicative notation, we refer to the group as a multiplicative group. Those terms might be used in a little broader sense by some people, I'm not sure, but that's generally the idea. And these terms should generally apply to abstract groups, but I think people probably use them for specific groups as well. Well, for example, the real numbers under addition are known as an additive group. So that's a concrete group that's an additive group. For rings and fields, when there's no specific notation, so for abstract rings or abstract fields, they have two binary operations. So one is referred to as, one is written additively, the other is written multiplicatively. Otherwise, there will be collision between the two and you'd have quite a bit of confusion. Now, there are some other commonly used notations and symbols. For example, for lattices, as discussed in Appendix B of the book, the two binary operations are known as meet and join. And this is the symbol for join, and this is the symbol for meet. They're generic symbols. They're used for generic lattices, but they also tend to be used in specific cases too. I don't think I've ever seen any other symbols used for meet and join, except in older books where union and intersection symbols were sometimes used. As we've discussed, in general, the algebraic operations that define a given algebraic structure have to satisfy certain properties. And that's part of the structure. Make no mistake about that. Okay, commutativity, associativity, whatever it is part of the structure. So here are some of the basic properties that we will encounter and that you will encounter in your study of other abstract algebraic structures. The most simplifying property of a binary operation is associativity. And so, since we're speaking in generic terms here now about abstract structures, here's the multiplicative notation, and here's the additive notation, the generic notations. This property is possessed by most of the common algebraic structures, addition and multiplication of numbers, functions, matrices, they're all associative. Union and intersection in the power set, associative. Meet and join in lattices, both associative. This is the property that allows us to write a product, in here multiplicative notation, ABC, without the need for parentheses. Life without associativity, and that does exist, even on this planet, especially for some kinds of rather complicated rings, is very much more complicated than life with associativity. So the subject of non-associative rings, and there are books written on that, is a very specialized field, studied not even at the beginning graduate level, but at the more advanced graduate level by those mathematicians who are specializing in ring theory. There is one famous example of an operation that's not associative, and that is the cross product of vectors in R3. In general, we do not have associativity, but I think at the relatively elementary level, that's the only example, certainly that I can remember, of a non-associative product. A second property of binary operations that does simplify life considerably is commutativity, which looks like this. But, as it would happen, many important algebraic structures have products that are not commutative. Multiplication of matrices is not commutative. Neither is composition of functions. It's the presence of commutativity, however, of a product that allows us to write the quantity AB to the nth power as A to the n, B to the n. And so when commutativity is not present, there's not much we can do with this expression, and that can cause considerable complications. As to properties of nullery operations, the most important and generally required property of a nullery operation is that it be neutral with respect to an associated binary operation. I talked about this briefly before. When additive notation is used for the binary operation, a neutral element is denoted by this symbol and called an additive identity, or zero, which is what it is, zero. When multiplicative notation is used for the associated binary operation, a neutral element is denoted by the symbol 1, or sometimes E, and it's called a multiplicative identity, or just the identity, which is a little bit dangerous, because in both cases they are identity elements. And here's the neutral property in both forms of generic notation. And we saw these at work with the monoids that we had before. But notice that two equations are necessary in both cases, because we don't know whether either of these, well, the binary operation here is commutative. So we need two equations in case it's not commutative. I think E is sometimes also used for a generic identity. So it could be 0, or it could be 1, or it could be something else. And that's not a bad thing. The most important, and again, generally required property of a unary operation is that it behaves nicely with respect to both an associated binary operation and an associated nullery operation. So in additive notation, a unary operation is generally denoted this way. A is mapped to what we call negative A. Negative A is the additive inverse of A. And the behavior we require is that when you add an element to its additive inverse, you get the neutral element, 0. Multiplicative notation looks like this. A goes to A inverse. This would be read A inverse. Better to call it the multiplicative inverse so there's no confusion. And the nice behavior looks like this. So you can see that because the properties of nullery operations are defined in terms of an associated binary operation, and the properties of unary operations are defined in terms of both an associated binary operation and an associated nullery operation, we can say that the operations are interlinked by their properties. They're not independent, generally speaking. Let's take a look at some examples of algebraic structures in very general context, informally speaking, so don't worry about the details. I just want to give you an overall impression. We've talked about these monoid structures already. As far as some examples of groups, the integers, z, have a well-known unary operation, the taking of negatives. And so this algebraic structure, carrier set, addition, this unary operation, which I called lambda, no particular reason, I like lambda, and the 0 element, that consists of a carrier set, binary operation, unary operation, nullery operation. That's what we need for a group. These operations do satisfy the properties required of an additive group. And we'll see that in detail in the next chapter. On the other hand, on the multiplicative side, the analog of taking negatives is taking inverses, multiplicative inverses. But this isn't defined for z equals 0, so we don't get a group. This operation of taking inverses is what you might call a partial operation on the carrier set. It applies only to non-zero integers. So we don't have a multiplicative group. Some quick examples of rings. Taking all of the common algebraic operations on the integers, so we get both addition and multiplication, we get this structure. So what we have here is a carrier set z, binary operation of addition, unary operation of taking negatives, and it looks like I didn't write this structure correctly. We need the third one is multiplication. So here, the binary operation of multiplication. Then we've got the unary operation of taking negatives, and we've got, oh, I guess I put it down here. I should have moved it up, because it would be a little more consistent to move it up to there. Okay. Anyway, we got the two binary operations, addition, multiplication. We've got taking of negatives, additive inverses, and two neutral elements, one for addition and one for multiplication. What's missing here is what we discussed earlier, and that is multiplicative inverses, because except for positive and negative 1, no other integer has a multiplicative inverse as an integer. This structure, however, satisfies the properties required of a ring. So the common language you will hear among mathematicians is considered the ring of integers. Similar analysis can be done for the functions, say from R to R. We have a carrier set of functions. We have, I guess I did it again, addition, multiplication, taking of negatives, and two nullery operations. In this case, it's the zero function, that's the additive identity, and the what is called the identity function, which is the multiplicative identity for this ring, the ring of real functions. A similar analysis can be done for matrices, and I think you probably already know how that would go. As to fields, the set of all real numbers has a very strong algebraic structure. Here are the details. You have the real numbers, you have addition, you have the taking of negatives, you have the zero neutral element for addition, you have multiplication, you have this function mu, which is a partial operation, the taking of multiplicative inverses on the non-zero real numbers, and then you have 1. This is the multiplicative identity. So here are the details. And these operations satisfy the properties required of a field. These operations can be applied or restricted to the rational numbers or extended to the complex numbers, and we still get a field. But it won't work for matrices because it's well known that a lot of matrices do not have multiplicative inverses, not just the zero matrix. Some fields have finite carrier sets, and these are called finite fields, and they are fascinating algebraic structures, very important in, for example, other areas of mathematics, such as the theory of error-correcting codes. The simplest finite field has carrier set Z2, which is just the integers 0 and 1, and the operations are addition and multiplication mod 2, the binary operations. And these are the tables for those. And I'll leave it to you to identify the appropriate nullery and unary operations in this case. This can be generalized to the sets ZP, where P is prime, and they are the integers from 0 to P minus 1. And addition and multiplication are performed modulo P in this case. So we do ordinary addition, multiplication, then reduce mod P. So those are finite fields. And there are whole books written on finite fields, and they're quite interesting, the properties of finite fields. Lattices, another algebraic structure we have some interest in. If S is a set, then the power set of S, which, as you know, I'm sure, is the set of all subsets of S, has two binary operations, union and intersection. And these operations satisfy the required properties to make P of S into a lattice. In fact, the power set also possesses neutral elements for union and intersection. The empty set is neutral for union. The entire set is neutral for intersection. And every subset of S, every member of the power set, has a complement with respect to S. So that defines a unary operation. And these operations have the necessary properties to form an algebraic structure known as a Boolean algebra, which is very important in logic and computer science and other places.